Hi guys, Mr. Kane here.
Hi guys, Mrs. Goswish here. Hey, what? Mr. Kane?
Yeah.
What is this on your board behind us now?
I didn't draw that.
Bow ties are cool.
Bow ties are cool.
Bow ties are cool.
Unfortunately, I'm not wearing a bow tie.
Not today.
No.
And what is that under there?
It says it's a call box, a police call box.
TARDIS, time and relative dimension in space machine. Fascinating.
By the time you guys watch this, you'll wish you had a TARDIS because the Doctor Who marathon will have been last weekend.
Yep. Oh well.
Sorry. If you have a TARDIS, you can go back in time and watch it again. Or if you have a DVR.
Yep.
Alright, so today we're going to be talking about three major components of the atom. Turns out that we know that the atom has been broken down into protons, which are symbolized with a p, lowercase p, with a plus as a superscript up in the air.
I was just going to ask you about that, Mr. Kane, because I'm a very lazy person. Yeah. I don't want to write protons, neutrons, and electrons each time.
Notice it's not p plus, it's p with the positive sign above.
So a superscript of a positive sign?
A superscript. That is super, like above.
Above.
Yeah.
All right. Good.
Okay. Neutrons are N with a 0 up at the top there. Now, some people like to just draw the O. I sometimes write a slash through my 0. It's part of, I don't know, computer programming. You said that.
Yeah.
But it doesn't really matter. Most people do it this way. That's fine.
Okay.
And then electrons are like this.
All right.
Okay. So we got three ways to abbreviate protons, neutrons, and electrons.
Good, because I'm lazy. I don't want to write it all out. Those little superscript things, what exactly do they tell you about the protons, neutrons, and electrons?
It reminds me of a story.
Ooh, I love stories.
A neutron walks into a bar, asks the bartender for a drink, has his drink, talks to the bartender, eats some peanuts, and eventually asks the bartender, "So what's my bill?" Bartender says, "For you, no charge."
Oh, God. That's terrible, Mr. Kane.
And what's terrible is that it's actually educational. No charge.
No charge
Zero
on a
charge.
neutron.
Okay.
Very good. That was pretty good.
Of course, it tells you that protons have a positive charge and electrons have a negative charge.
All right.
Okay. All right. So this is our current model of the atom.
Okay. Nucleus, yeah.
Yep.
Smack in the center.
We got this nucleus here, and we've talked about what's wrong with this nucleus in class probably by now.
Yeah.
If we haven't, make sure to ask about that next time, okay? Nucleus has the most amount of mass of the atom. It's where all the protons and the neutrons live. And we have these other circular orbits around the outside.
Protons, neutrons. That center thing, isn't it more like a cherry pit kind of a deal?
Oh, yeah, this
right?
is kind of like a cherry pit. It's really small, right?
Okay, yeah.
And then the circular orbits here that are going around on the outside, these circular orbits that you see, that's where the largest volume is taken up of the atom. You know, it's space. There's nothing there.
Okay.
The
electrons are there, aren't they?
Yeah, that's where the
the
electrons are, and they
mass.
have the smallest mass.
If you lose electrons to an atom, does it alter the mass of the atom at all?
Tiny bit? Not a lot.
But not enough to warrant changing the mass of an atom if you're an ion, right? The mass of the atom would stay the same.
Yeah, pretty much.
Okay.
I don't think it's not going to change significantly.
Okay, that's small. Loss or gain of an electron will not change the mass of the atom.
So our current model of the atom, just to draw another analogy here, if the nucleus is the size of a period that's in a textbook, I thought this was kind of interesting. You do the math, and you find out if the nucleus is the size of a period, the edge of the atom is going to be 2.5 meters away.
Wow.
So that's quite a distance. 2.5 meters is nearly 3 yards.
Yep.
Yeah. All right. I think we talked about this. Protons and neutrons are in the nucleus. Electrons are in those orbitals.
Okay.
The neutrons bind protons together. There's something called a strong nuclear force. It's kind of the nuclear glue. So the neutrons are holding all those protons to each other, because when you think about it, all those positive charges in the same place, they'd want to repel each other.
Yeah.
So the atom should just fly apart. But if you get enough neutrons together with those protons, they glue each other together.
Okay.
And most of the volume of the atom is empty space. Oh, there it is. Protons are 2,000 times the mass of an electron. So if you lose one electron, no big deal. You lose a proton,
yeah, that's
which is
a big
kind of
deal.
hard. Which is kind of hard to do anyhow. All right. Oh, by the way, guys, we told you that Millikan was responsible for something. This is what Millikan's responsible for. He figured out that the mass of the electron is 1/2000th that of the proton.
He did the charge to mass ratio and found the mass, didn't he?
Mm-hmm.
That's a real big difference. 2,000 times more massive than the electron.
So here's our summary of subatomic particles.
Okay, let's see. We have the electron, proton, and neutron. The symbol is the electron with the little negative or minus sign. Protons with the little positive. The neutron is the no charge, so it's a little 0 or naught. -1 charge, +1 charge, and 0 for the neutrons. And then the masses is, wow, look at the difference in the mass between the electron, which is 10 to the -31st, and the proton, which is 10 to the -27th. Oh, and look, the protons and the neutrons are exactly the same mass. That's nice.
Oh, hey, check that out. Yeah, 1.673 and 1.673 times 10 to the -27.
Up the bulk of the mass of the atom because of their size.
Do I have to memorize this number, 9.109 times 10 to the -31st? Is that useful?
No, we don't really use it much. Just know that the electron is not imperative to the mass of the atom. Because when we start dealing with ions, and you're still dealing with atomic mass, loss or gain of an electron does not change the mass of the atom.
Okay, and this means about 0, right? It doesn't
Correct.
mean squiggly line 0.
The squiggly line means approximately.
Okay.
They're close to.
And this is exactly 1, and that's exactly 1.
Yep.
What's the AMU stand for?
AMU is atomic mass unit, and it is an arbitrary unit. Scientists picked it to represent a really, 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 really small amount, because you're going to get really tired of writing 1.673 times 10 to the -27 every time you talk about the mass of a proton or a neutron.
Yeah, and if I talk about like carbon that has 6 of those, I'm going to have to do some math and multiply it by
Yeah.
6. It's easier to multiply 1 times 6 than 1.673 times 10 to the -27 times 6.
Yep, the AMU
Yeah.
just gives you more aesthetically pleasing numbers.
Okay. All right, here we go. Reading the periodic table. If you haven't noticed yet, guys, your periodic table looks like this. Each of the tiles gives you a certain amount of information. Up on the top is the name. We get an atomic number, which is always an integer meaning a whole number.
Yep.
The symbol, which you can see here, C.
Some of the elements have one symbol to represent them. Some of the elements have two symbols, correct?
Right, yeah, so if this was copper, it would be a lowercase symbol after the uppercase, right?
Yes.
Okay, but this is not copper, so I should probably... the average atomic mass is usually a decimal, 12.01 in the case of carbon. And is that .01 important?
Oh, yes. We're always going to have our masses from the periodic table to end 2 digits right of the decimal.
And then our electronegativity here that we'll use is, well, we'll use this eventually. For now, this number is kind of meaningless for us. We just kind of want to ignore it.
Okay.
Okay. If I haven't already done so, my first assignment with the periodic table, if you already got it, you should have already memorized the first 36 element names and symbols.
Okay.
Yeah. Right.
What do these mean? The name is the official name given to the element. The symbol is the official symbol given to the element. Sometimes it's similar to the name.
Like in the case of carbon.
Carbon, yep, C, carbon. Very nice and simple. Hydrogen,
Carbon.
H.
Hydrogen, yeah.
Lithium, Li.
Oxygen.
Oxygen, yep, there's
Yeah.
a couple of them.
Lithium's like that.
Not brain surgery to know some of them and connect them to.
What about like AU?
AU, I don't know what that is, Mr. Kane.
I was downtown last night and I heard somebody yelling, AU, give me back my gold!
The AU is the older name for gold, which was, if I remember right, what was it called? Aurorium or something like that?
It was aurum. I took
Aurum?
Latin in high school.
Okay, so Latin name for gold. We don't use it anymore, but we still use the symbol AU. And
Yeah, things like silver and AG and
Yeah.
W, wolfranium.
Well-
well, it's not wolfranium anymore, is it? Tungsten.
tungsten.
Yeah, tungsten is W.
Well, think about it. What about sodium? Sodium you'd think would logically be SO, and it's not. It's
It's
Na
Na,
for
yeah.
natrium.
And the first letter's always capitalized, right?
Yes, first
And-
letter is always capitalized. The second one is always lowercase, if there is a second one.
And do I actually get it wrong if I put this?
Yes,
Oh.
that is wrong.
Okay, so that's nitrogen and some other element that hasn't been discovered yet with the
Yep.
symbol A.
Yep.
All right, so I don't want to put na, I want to put na.
Yep. Oh, and could you do me a favor, Mr. Kane?
Yep.
Write down the symbol for chlorine.
Over here,
Yeah.
C, L.
That's Cl, not C1.
So we've also got our atomic number that describes the number of protons in the nucleus,
Mm-hmm.
which is kind of cool because it's the inside of the atom. I like to think of it this way. It's the inside of the atom. It's the heart of the atom. and it tells you exactly what that atom is.
So every element will have its own specific atomic number. No two elements will have the same atomic number.
Carbon. If somehow an atom were to a proton and it only has 5, it would suddenly become another element. It would actually become boron, which is what we're doing here.
Boron. Okay, so we're moving on then.
We're boring on and on and on. All right.
Elements versus isotopes. Average atomic mass. It's not a whole number. If you look at your periodic table, you will see a bunch of average atomic masses with decimal places. That's because it's a calculated average. Dalton said all atoms of an element are identical. He was not correct.
That was one of the red ones.
Was it one of the? Oh yeah, it was.
Remember there were 2 that were red?
That's right. The atoms of the same element might have differing number of neutrons. Those are called isotopes.
Okay. And so when you look at the periodic table, you see carbon has 12.01. What are my chances of finding an atom of carbon that has exactly a mass of 12.01?
0. It's a mathematical computation.
Okay, so it's just an average.
It's just an average.
Okay. What if, on the other hand, I know there's several isotopes of carbon. There's
4 of them.
Carbon 14.
Correct.
Is
13.
one of them.
Yep. Carbon 13.
There's a carbon 13.
12.
There's a carbon 12.
And I think a 15.
I believe there's an 11.
Is it
also.
11? Yeah.
I think it's an 11, and there's also a carbon 15. So there's 3 different kinds of carbon, and they come in varying amounts in the world. When you add up all the masses and do the math to find out the average, you find out that it's 12.01. The atomic mass is a whole number, so what I've actually been writing down here are atomic masses. Those are whole numbers.
Okay.
Right? And a neat trick here is that the number of neutrons can be calculated by taking the atomic mass minus the number of protons. So say for like carbon 14, the atomic mass is 14. So if I'm going to do the math here, I'll do it right here. 14 minus the number of protons.
Now how do you know the number of protons?
Well, that's the number in the heart. That's the atomic. So 14 minus 6 will give me the number of neutrons in carbon 14. Let's see. Do a quick math. 8. Mm-hmm. Okay. So it has 8 neutrons and 6 protons.
Okay, and that's the isotope 14, carbon 14.
Right. That's carbon 14. Now, on the other hand, carbon. Let's go for a low number like 11. Carbon 11 has an atomic mass of 11. It also has 6 protons because it's carbon. 11 minus 6 is 5, so its number of neutrons is 5.
Oh, so different number of neutrons. So isotopes must have different number of neutrons. Okay.
And what's interesting here is that carbon 14 is radioactive.
Oh.
Whereas carbon 11 is not so radioactive.
Okay.
So when Dalton said that all atoms of the same element are identical, he was wrong.
Right.
One type of carbon is radioactive, whereas another type is a little bit more stable.
Okay. And
X would represent the symbol.
uh-huh.
A would represent the mass number.
Yep.
And Z would represent the atomic number.
Correct.
So it was just like we were doing on the other page there.
Yeah.
Chlorine.
Oh, there's our C1.
With a C1. You sunk my battleship.
Yeah, really.
Or did I get bingo? I forget which game we're playing. Chlorine has an atomic mass of 35, and it has 17 protons. That's what this means.
So they kind of set it up. You can actually, that's like a math problem, isn't it? If you wanted to find the number of neutrons, isn't it 35 minus 17?
35
Well,
minus
that was
17.
nice of
Well, let's see. We borrow,
Yeah.
and we get an 8 here, if I remember right. And we get 18 neutrons and 17 protons.
Wow, nice of them to set it up that way.
A little shorthand notation. Press pause and see if you can calculate protons, neutrons, and electrons. So let's go through this real quick. Miss G, can you tell me how many protons we got?
Let's see. The number of protons is the atomic number, so that would be the 8.
All right.
So there are 8 protons.
8 protons. All right. Neutrons.
Number of neutrons would be the mass number, or at least the average atomic mass rounded, so it would be 16.
Oh, that's nice. Rounded at 16.
Yeah.
16.00 rounded is
Right,
16.
16 minus 8, so there must be 8 neutrons.
8 neutrons.
So the number
I should
of
probably
them-
put units on these, shouldn't I? 8 protons, 8 neutrons, and
Well, since it's just the element and it's neutral, 8 protons positively charged, in order to be neutrally charged or a sum of 0.
I can do this math.
There you go.
8 electrons and 8 protons means no charge.
Correct.
All right, so protons here, this one's going to be simple. 80 protons.
80 protons.
And to do neutrons, I have to round this, 200.59.
So the correct rounding would be what?
Well, the 5 tells me, I want to the ones place because I want a whole number.
Correct, you want a whole number.
So I'm going to go by the 5. The 5's going to tell me to round this one up.
Okay, do you have to do anything with that 9 to the right of the 5?
Am I allowed to round twice?
Nope, you are not.
Can I round twice on my paycheck?
No, you cannot.
All
So
right,
that
so-
9 is superfluous.
So I've got 201 as my mass, and I'm going to subtract 80 protons from that. And I am going to get 100, and in my head, 21. And if we want this thing to be a neutral atom, it has to have the same number of electrons as it has protons.
Okay.
Oops, and I
wrong
labeled that
symbol.
wrong. Labeled it wrong, so wrong answer, so I should say 80 electrons. All right.
Ions.
You're going to get a charge out of this.
An atom that has a charge is an ion. How do you know if an atom has a charge, Mr. Kane?
Well, I usually check the credit card statement.
How do you know that an atom has a charge?
All right. So you tell that an atom has a charge by just looking in the upper right-hand corner there. You see it says 2 positive and 1 positive? This means that magnesium here, it's actually lost electrons here. And you have to kind of think about that. And there's 2 things to think about. If we're drawing magnesium, magnesium's got all these protons in the center, right? Along
Yep.
with its neutrons?
12 protons in the center.
Okay, I got exactly 12. Can you count those?
Yep. 1, 2, 3, 4, 5, 6, 7, 8, 9,
Yep,
10,
I got 12. And then we got enough neutrons there.
Okay.
And magnesium also has these energy levels, these orbits, to hold its electrons. The electrons are whizzing around in these energy levels. Question is, can I change the number of protons
No.
to get a charge? It's going to be very difficult to get in there to change the number of protons because these electrons are moving around near the speed of light, and you're going to get hit by one of them if you try and get in there.
Yeah.
So the only thing that we can really do is we can affect the number of electrons that are in these orbitals. And it turns out that magnesium likes to lose 2 electrons. What you have to do is you have to think about it this way. You're losing something that's a negative. So you're losing a negative electron, and that's happening twice. You're losing 2 negative electrons.
Okay.
When I subtract a negative in math, they've taught us that subtracting a negative is the same as adding a positive. So I'm actually adding a positive, so I get a 2 positive charge here.
Okay, so in other words, you start out with 12 electrons in the neutral atom and 12 protons.
12 protons and 12 electrons. I like this better.
And then, according to the charge, you've lost 2 electrons, so that becomes a 10.
Yeah.
So if you have a positive 12 and a negative 10, that gives you a charge of plus 2, correct?
Right, a positive 12 and a negative 10 is going to give me a positive 2.
Positive
yeah.
2. So the
2
charge.
plus.
Oh,
These are called cations.
okay.
Okay, the way I like to try and remember it is a positive charge kind of looks like the letter T here.
Oh, that's a good tool.
So that's positive, a T,
All right.
cations.
I like that.
Anions, the other kind of ion, doesn't have a T in it. So this happens to be pretty decent.
Okay.
All right, now anions get a negative charge, and that's because they wind up gaining electrons. So oxygen here in this example gains 2 electrons. Oxygen usually starts out with 8 protons and 8 electrons.
So the ion still has the 8 protons.
Still has the 8 protons,
But now it has 10 electrons.
but now it has 10 electrons. So if you do the math on this,
So plus 8 and a negative 10.
plus 8 and a negative 10, that's going to give me
Mathematically a negative 2,
a
yeah?
negative 2, yeah.
And that's the
Which-
charge.
Which we always write it as 2 minus rather than the negative
yeah,
2.
yeah.
Okay.
Well, and that makes sense too. That means that the more electrons you gain, the more negative you get, correct?
Right, that makes
Okay,
sense.
that makes sense.
Now here's the fun part, guys. Fluorine gets a negative 1 charge, and one of the rules in chemistry with superscripts is that you don't have to write a 1, so quite often you'll see this written.
Okay, the 1 is understood.
The 1 is understood. If it's a negative charge, it's got to be -1 if you didn't write how many.
Okay.
Same thing for positive charges. So lithium happens to be +1. You don't have to write the 1.
It's understood.
It's understood. You can write just the You can write it both ways, neither way. I don't think I mark either way wrong.
No, nor do I.
Okay. And a nice way to remember that anions, another trick here, it doesn't actually mean it, but a negative ion
Sounds like anion.
is we're going to ask you to fill in this table and bring that to class with you.
Write it out nice and neat on a piece of paper with your name and your period, and bring it to class the next day.